Okay. So, oops. Oh, where'd you go? Where'd you go? Oh, there you are. I'm going to, sorry. We're going to finish or continue on in our discussion of intermolecular forces. This time, we're going to actually look at how those forces relate to physical properties. Okay. And so basically, you can predict relative properties such as boiling point, freezing point, viscosity, vapor pressure is one that likes to pop up. And so I'm going to go back here to, oh, there's my messages. Go back to our notes. And let us make a new note. And this note, why did I make it so small? My screen's so small. We're going to call this intermolecular forces. We'll say IMFs and physical properties. All right. All right. We've already talked about the IMFs. We've got linear dispersion forces, dipole-dipole forces, and hydrogen bonding. We watched the video. We understand. We asked Miss Murphy what our questions are. Or we looked it up and figured it out ourselves. And here we are looking at how we would apply that, okay? What physical properties are we talking about? We're talking about boiling points, right? We're talking about freezing points. We're talking about vapor pressure is very common one to see. And those are the most common. We could talk about, I think we're just going to kind of leave it there, to be honest with you. If something else pops up, I'll bring it in, okay? Or if I think of something. Now, if we have boiling points, think about it. Think about it, right? I'm going to draw my thing. Solid. Right, to liquid, right, they're close to gas, right? Well, we add heat, right? So boiling, as you know, but you got to think about it this way, occurs here, right? This is what boiling is. It's going from the liquid, right, obviously, to the gas with the addition of heat, right? So in order to turn the liquid into the gas, right, that says plus heat. In order to turn the liquid into the gas, for boiling, I'm going to write this, boiling requires completely overcoming, right, all intermolecular forces of attraction, right? In order to boil a liquid, you must take that liquid, right here, and you must overcome all the little attractive forces that are between all of these molecules, right? They're not bonds, they're forces, but you must overcome all of them in order to turn that liquid, all of it, into a gas, okay? So what does that mean? Well, that means this. The stronger the IMFs, stronger IMFs relate to higher boiling points, right? More heat has to be added to overcome those intermolecular forces. So we have higher boiling temperatures. Okay. Now, okay, I'm going to leave it at that. Freezing points. Let's look at freezing points. We're going to look at it a little bit differently, okay? Because we're going to go backwards this time. And we're going to remove heat. So if we are talking about freezing, right? Let's take let's take our arrow to here, right? And we'll go this way. And in order to turn, right, the liquid to the solid, we must remove heat, right? We don't cool it, we remove the heat. All right, now I want you to think about it like this. I've got a liquid. As I remove heat, those molecules condense and come closer together. The greater the attraction between those molecules, the stronger the forces of attraction, the easier it is to form that solid. The easier it is to form that solid, the less heat that has to be removed. So we end up at a point of freezing that is actually higher when we have stronger attractive forces. We don't have to get it as cold to push those particles together as they are in the solid state. So what we see, I'm going to write it kind of like I did up there. Freezing brings molecules together, right? The greater the attraction, those molecules for each other, the less heat that needs to be removed. I don't know. Maybe I should have wrote that needs to be removed to solidify the substance, right, to form that solid, resulting in higher boiling points. So if you can always picture this, create this picture in your head, you can figure it out, right? You can figure it out. Am I pushing them together? Am I pulling them apart? If I'm pulling them apart, I have to overcome it. The stronger, the harder. If I'm pushing them together, they want the stronger, the greater the attraction, the easier that's going to be. And then ask myself, well, am I taking the heat out and it's going to be harder or easier? Or am I removing the heat and pushing them together? Is it going to be harder or easier? Now let's talk about vapor pressure. And I'm going to have to draw a picture here, okay? So let's look at vapor pressure. Let's understand what it is. If I have a liquid sitting here, right? Let's cover this up. I have a liquid here, right? Well, this is my liquid, right? And it's just chilling, just chilling. Well, you know that some of these liquid molecules are going to escape to the gaseous phase, right? It's going to be the ones on the top because they've got less holding them down, right? You want to kind of see this like this. Right? These are all the particles, all the molecules that are loosely attracted to each other in my liquid. And you can see that the further down a molecule is, oops, I don't want that. Sorry about that. The further down a molecule is, the more particles it's attracted to and it's stuck in place. So, right, but some of these are going to escape. They're going to break free and they're going to float at top as gas particles, right? And you can see why it's going to be those at the top. It's easier for those to break free. Now, technically, students, boiling occurs. I remember being a little older than you learning this. Boiling occurs when the particles on the bottom have enough kinetic energy to make it all the way to the top. that is when your boiling starts happening and you see it. So you want to see in your pot, the bubble go from the top, from the bottom of the pot all the way to the top. And at that point, you have established boiling. Okay. Anywho, vapor pressure is the pressure caused by the gas particles of the substance that have evaporated, right? We're not really talking about boiling, we're talking about evaporated. So the ones on the top that have evaporated and are now gases, right? I'm writing more than I normally do because this is 20% and are now gases, sorry, and have a pressure because gases exhibit a pressure, exhibit a pressure, right? They collide on the walls of their container, thus causing a force to be hitting on the walls of the container, and that's their pressure. Now, the more gas particles, right, the higher the pressure. Okay, so we're about to end this here, okay? The higher the vapor pressure. We'll see how that works. So let's once again envision our, I'm sorry, I have to redraw this. I can't keep looking at it. It's killing me. Let's envision our flask, which is closed. We have another flask, which is closed. This one has a liquid, which has weak IMFs. This one has a liquid that has strong IMFs. Okay? Well, let's think about what's going to happen. If I have weak IMFs, doesn't that mean that I could more easily escape the liquid phase and enter the gaseous phase? So we're going to have more gas. Where I have strong IMFs, it's going to be harder for my molecules to leave the, I'm going to clean this up because it almost looks good. Oops, let's not do that. I'm going to, hold on. I kind of want to make this look better. I'm into this right now. Okay. Where I have the stronger of the IMFs, right? Weaker, I'm going to have a lot of gas particles. I'm going to have more gas, higher PVAP, right? That stands for vapor pressure. PVAP, pressure of the vapor, okay? And here I have less gas. So I have a lower PVAP, as in vapor pressure. Okay? Let's look at our PowerPoint. Let's apply that, all right? Let's apply this. Let me go here, let me go here. Let's just kind of look at some things together. PowerPoint. Actually, no, I'm not going to do that. I'm not going to do that. I'm going to go ahead and end this, and we're going to talk about that in class. We're going to look at a PowerPoint in class together. Okay. So that would be intermolecular forces and physical properties. I'm going to leave it at that. Okay. Forget what I'm supposed to do. End.